Okay, so now we already have everything, more or less, because we already have discussed in fluid dynamics when we really consider the compressible flow. We have the vertical structures as well as the longitudinal structures, which are wave propagation. And we have seen for a simplified perturbation ansatz, we get out the wave equation. However, we want to have some models for aeroacoustics in the sense that it's a too high burden in really numerical compute the full set of compressible flow equations. And on the other hand, what we then get is a result, which is the pressure, the velocity, where we cannot differ which part is the vertical part and which part is the wave part. Okay, so as you see on this slide, we will start with Lighthill's idea. It's also called Lighthill's analogy. And this is really the starting of aeroacoustic, a very great idea. We will see with just some rearrangement we get out from the fluid dynamics equations, a wave equation. Lighthill at this time was interested in the noise being generated by airplanes in this sense. However, he could not solve clearly for this problem the partial differential equations numerically, so he transformed it to an integral equation by the free field Green's function, which means with his formulation in the integral, this integral formulation, it was not capable to take into account any solid bodies and obstacles, which are clearly there when you look at this problem at hand of the noise being generated by a plane. And Curl extended it to really show how you can take this also into account in the integral formula. For the partial differential equation with the correct boundary condition, Lighthill is really the mother of all equations we have here. And then other researchers like Powell or Dowling, for example, tried to get more insight what is really the source, and they came up with the so-called vortex sound. And that is what I already told you sometimes, that really each vertical structure is generating a wave. And just recently means it was in the 19th beginning of this century, some came up with perturbation ansatz, and therefore really we will speak also about so-called perturbation equations, which at least in a low Mach number regime really makes sense, because we can really separate the flow from the acoustics, know exactly what are the sources, and also have the interaction term within our partial differential equation. Yeah, and we will conclude with some comparisons. So for a simple case of a cylinder in cross flow, to have all the different models in hand and look what are the results and how we can compare them. Okay, so what is the goal now of this chapter? The goal clearly should be in this sense that you understand the source mechanism, how waves are generated by flows, and you have then at hand different models, because for each problem at hand you should choose the most appropriate model. So there is no general model at hand. Clearly the general model would be to solve the compressible flow equation in all details, but for practical application this is not feasible. And so we need models, and we should know what are the restrictions of the models in order to choose the correct one. Yeah, and this is here a very nice example of a ventilator. You see here just the rotor, and what you see here are structures of the velocity. And yeah, if you have more or less then the job to do for a new prototype, such an aeroacoustic simulation, then clearly you should already know, let's say, something from physics, yeah, what effects occur there. And in this case, if you have this knowledge, you can choose the appropriate model, which we will discuss in this section here. And then, very importantly, clearly will be always, as it is the case for all numerical simulation, to have good visualization tools and also to compute post-processing results like the vorticity, for example, which you then can visualize and get a more detailed insight. What are really the flow structures? What are the sources? How the waves are propagating? Because this is something which is very difficult with measurements. You will be very restricted. Clearly, we can measure with microphones or with pressure sensors at some distinct points, but you will never get the resolution in time as well as in space as it is possible with numerical simulation. On the other hand, we always have to keep in mind that simulations are simulations of models. We never have reality. And so a combination of, let's say, measurements and simulations are always a good idea. Okay, now let's jump in. And when we were discussing the compressible fluid dynamics equation, especially the conservation of momentum, then we also introduced the so-called momentum flux tensor as written explicitly here, where we have here the so-called Reynolds term. We have here the pressure difference to the ambient pressure, and we have here our viscous stress tensor. And with this substitution, with this pi tensor here, the so-called momentum flux tensor, we can write down in a very elegant way the conservation of momentum, where we have the time derivative, the partial time derivative of density velocity plus the space derivative of this tensor. Again, what you see here, it is a vectorial partial differential equation, because here it's quite easy to see it. V, the velocity is a vector. This is a tensor of second order, and the first order spatial derivative, actually the divergence of a tensor of second order, gives you a tensor of first order, which is a vector. Now, in a first case, the idea of Lighthill was to investigate the case of no flow. So if we have no flow, then clearly our velocities can be set to 0. And as we know, the model for the viscous stress tensor is the gradients of the velocities, and they are scaled with the viscous characterization of the medium at hand. So in this sense, this term will be 0 as well as this term will be 0, and the only remaining term is exactly this term. And he introduced now with delta, the delta function. So with this delta function, it is then also a matrix 3 by 3 in 3D, or tensor of second order. And he just introduced here this relation to the density via a constant value. At the end, it's the speed of sound, but it could be any constant here. And as you see, due to this dot, what we have here, it means this is really constant. Okay, now when we substitute this relation now here in our general conservation of momentum, we get out here this equation. We have here this simplification of the momentum flux tensor, here rewritten by the fluctuating density. That is also a very important thing. So we call the difference between ambient quantities fluctuating quantities. So for us, we call this the fluctuating density. So it changes over time. And now you see why we rewrite it, the pressure fluctuation as a density fluctuation, because we also have to consider the conservation of mass, which is here in general form. The only difference what has been made here is that we also have here the fluctuating density. Now the question is, when we introduce instead, because actually, as you know, this would be just the partial derivative of the total density. So is this correct, or do we have made here any simplification? What do you think? Instead of the density, we write here the density minus the ambient density. You can also write something to the chat. Don't want to switch on their microphone. I should perhaps write here. So when we have this zero index, means we have a constant quantity in space and time. So are we allowed to put here, instead of the density rho, the term density minus mean density? Exactly. Yeah, thanks for your comment. Exactly, since the mean density is constant both in space and time, we don't have changed it. So it is important to really stress this part. So there are not any currently approximations what we do. Okay, now we have these two equations, and as you know, we now do the same tricks as we have done for getting the wave equation. We want to get rid of these terms. So the derivative in space as well as time of density times velocity. And in this sense, it's clear what we take here is to do here a space derivative and to do here a time derivative. And when we subtract the resulting two equations, we come up here to the so-called homogeneous wave equation, again for our density fluctuation. Okay, now important is what we see. We have zero on the right hand side of this partial differential equation. Initial conditions are assumed to be zero, which means that what we will get out here is that the fluctuating density is equal to zero for all times, since we have no sources and also the initial conditions are zero, and we assume clearly according to the boundary condition, we at the boundary of our computational domain being very far away, this density fluctuation is also zero. Okay, so this was the case, again, importantly, of no flow. And since we know that when there is a flow, we can also hear generated sound. And that was then the idea of Lytle to say, okay, in the case of a flow, the difference of the total momentum tensor pi minus this tensor at no flow are the sources which are generating sound. Yeah, and so you see this is the long expression we have here, and we call this here with Lig, so it's also a tensor of second order. Okay, so what is now the next steps? Light-Hill did is clear because he again investigated in the momentum equation. And please have a look here that this term also pops up on the right hand side, which means that we could cancel this out and we have our initial momentum equation, conservation of momentum within any approximation. Yeah, if we go back here, as you can see here, this is our momentum equation. And if we go to this rearrangement, this term cancels out. If we put then this term to the left-hand side, we just have the conservation of momentum. So there is no change. The only change which we have done here is that by this trick, we now can rewrite again this momentum tensor for no flow, yeah, where we get in our density fluctuation. And we can rewrite here the difference of the momentum flux tensor at flow state minus no flow state. Yeah? And so we get already in here our Lig, which is called the Light-Hill stress tensor. Okay, so we have this reformulation without any approximation. We take our conservation of mass, the same as we did before. Yeah, and again, we want to get our wave operator, which means we will do here a derivative with respect to xi, here a derivative with respect to time, and we subtract these two equations. So we again get, as in the case before, our wave operator for the density fluctuation. And now we have a right-hand side, different from zero. And this is to be discussed, what this right-hand side really is. At this step, let's say these are sources. Yeah? As we are always defining the right-hand side of a partial differential equation, these are any sources in the domain which then gives us the solution at the end for the density fluctuation. Okay, so let's have a more detailed view of the ideas of Light-Hill. And let's look what we have here. So this Light-Hill tensor, yeah, has in here the density fluctuation. It also has in here pressure fluctuation. And here I write it as total velocity. So there is no separation between vertical part and wave part. So no separation between vertical and longitudinal part. As we know, we have a Helmholtz decomposition where we can decompose it in a vertical part, which is then described by a vector potential and is a kind of a really the vertical structures of the flow, and the longitudinal part we can describe by a scalar potential, which includes wave parts in it. Okay, which means this interpretation here that these are sources is not correct. Yeah? So therefore I cancel this out. This is a right-hand side. But as we see, the right-hand side includes also our solution variable, the density fluctuation. And we have some relation to the pressure fluctuation, so they are related. So it also includes here the variable for which we solve. And also this term cannot be a pure source term, because for the wave operator, we want to get the wave propagation and even wave paths are included here, yeah, due to the fact that this is the full compressible flow velocity. Yeah, and in this sense, yeah, we can really say that this so-called right-hand side term includes even acoustic nonlinearities, yeah, which are nicely, for example, seen here. Yeah, when we decompose this in a vertical part and a compressible part and associate the compressible part to the wave part, we have here these multiplications. And we also have here the total density. Don't forget, yeah, the total density is, as we know, is the mean density plus the fluctuating density. Yeah. So this is fully included here. Further on, it also includes, since we have this interaction, yeah, in this fluctuating part, yeah, there are flow parts and wave parts. The same here for the velocity and so on. So that will also include convection and refraction as we have when we have sound waves going through a flow. And since also viscosity is in, yeah, and the viscosity more or less models attenuation of the propagating waves. So summarizing, we can say we have a reformulation of the compressible fluid dynamics equation in a wave equation as shown here. However, we do not have any separation in this equation here between the flow structures and the wave structures. And therefore, the main challenge when you want to solve this wave equation as written here, as written down here, well, we first have to solve the full set of compressible flow dynamics equations in order to be able to get the Lighthill's tensor, yeah, as we see here. So actually we don't have gained anything. We still have to solve the full set of compressible flow dynamics equations. And we should have in mind that we have no separation between sources, between the interaction of the flow with the waves and the pure wave propagation. So this is a nice reformulation. However, the practical application in a general setting is not really feasible. Now my question, do you think you could think of problems where it makes sense? Yeah, because perhaps there the flow is constricted to a small domain. So we have to solve there the full set of compressible flow equations. So we can resolve all the scales. We put this into our wave equation and then solve for the density fluctuation very far away of where you have your turbulent flow. We have an idea where this could be of interest. Any example? It is actually the case I already have told before, and which was also investigated more or less by Lighthill, in this sense that, let's assume an airplane. Clearly, the flow computation will be a high challenge, but it makes no sense to take all the ambient air till the first houses of a airport into account when takeoff or landing of the airplane. So here it would be application when you would be able to solve there the flow equations, get then the Lighthill tensor, and then solve this equation. And here it would be even interesting not to solve it with any volume discretization method like finite element method or finite volume method, but with an integral equation, because the first houses will be far away and we are interested what is the noise, the sound there, the sound pressure level at these large distances. Okay, yeah, there is also nicely a hint in the chat. Thanks. Exactly, this is really a nice application. Okay, so in this sense, we have a first model which is even exact, but we see for most problems perhaps not really applicable due to the high computational effort you have to do in getting this Lighthill tensor. Okay, that means we should go into more details, and a first very interesting regime of flows is when we can restrict our problem to low Mach numbers. Yeah? So we know the Mach number is our characteristic velocity over speed of sound. And if this characteristic velocity in your application, which is, for example, the axial or radial fan, for example, then we can restrict here perhaps to practical applications where we get more insight in this Lighthill formulation. And there was very interesting theoretical works on this, in this case, that one has considered a single vortical structure, a eddy of size L, generating acoustic waves of wavelength lambda, and the whole region here, the whole region where the sound is generated has a length capital L. And the problem can't be solved for low Mach number, and we know when we have low Mach number, you can more or less describe and model the flow as an incompressible flow, where we know that the density is constant, and therefore the conservation of mass can be written simply by the divergence of the velocity zero, where we very often write this as the divergence of a velocity with index IC for incompressible equal 0. And where now for this problem we have a matching of this characteristic geometric dimension L over the size of the vortical structure being approximately 1. So we concentrate around the vortical structure there, and matches the compressible eddy core scaled by L to the surrounding acoustic field, which is clearly scaled by lambda. And if you do this by the help of asymptotic expansion, you get out that the main driving term within Lighthill's tensor is this part here. Yeah? So since we consider incompressible flow, the density is the mean density, And instead of the total velocity, we can restrict here to the incompressible velocity components, which fulfill that the divergence of the incompressible velocity is equal to 0. And we know that such a physical field can be described by a vector potential, exactly the curl of a vector potential. And we have there the vorticity, which is always given by the curl of the velocity. And since we just have an incompressible velocity, it's the curl of the incompressible velocity. So that means, since we consider an incompressible flow, we cannot take into account any longitudinal structures, so any wave structures. Therefore, we have a full decoupling between the flow and the acoustic waves, which means we can first perform the flow simulation, because this flow simulation is restricted to the set of incompressible flow equation, which do not take into account any wave structures. We then can compute our light-hill tensor, which is now really a source term. This is really a source term because this term does not include any wave structure and also does not include in this sense any density fluctuations for which we then solve the wave equation to get the acoustic propagation. So if I go back here to our general equation, we see that this is our wave operator for the density fluctuation. And this is now really a source term, the second spatial derivative of the light-hill tensor, in this approximation for an incompressible flow given by this term. And that we can compute. So that means also we have a pure forward coupling. So perhaps the flow influences the waves. They are the sources for the waves, but we have no coupling back from our radiating waves on the flow. And therefore, importantly, this is a pure forward coupling. And there are also problems which are of great interest, even for low Mach numbers. For example, a cavity flow. So I write here something like this. This is a cavity, and here you have some inflow. This is the cavity. And here it could be the case that we have a strong coupling back from the acoustic waves being generated here by this cavity flow on the flow itself. So this is something which we cannot consider, because we have a forward coupling. Okay, but for a lot of problems, let's consider this axial fan, radial fan. It is really a good choice to do as written down here, the incompressible flow simulation, compute the sources, for example, by this model here of light-hill, and then the wave propagation. Further important properties which can be used and which are very important for the numerical computation is that when we consider this reduced light-hill source, which is written down here, then you can show that this second spatial derivative can be rewritten by this term here, where you just have first order spatial derivatives due to the fact that we have the property that the divergence of the incompressible velocity is zero. Why do you think is this important? for example, that you do not evaluate here the second spatial derivative of our approximated light hill tensor, but to do it in this sense. Do you have an idea why this is very important in practice when you do numerical simulations?
Maybe for the weak ansatz or the weak form of the PDE?
Yeah, that's the idea with the weak form, yeah, because you know you also multiply the source term by a test function, you can then apply integration by parts, that's correct. But it would be not necessary to do integration by parts, yeah, because this is the source term and not a part of the wave operator. But what do you think about the accuracy? Yeah, you have to consider the accuracy, and this velocity here has been numerically computed, not analytically. Yeah? We solve it by the finite volume, finite element method, whatever. So you solve the partial differential equation for the incompressible flow equations, and you perform a spatial derivative. Perhaps you have some experience for finite difference. It's also the same case for finite difference method. So whenever you have a numerical solution, and in a next step you compute a derivative of this numerical solution, you will almost lose one order of accuracy. Yeah? And therefore, it's clearly not good to have second order derivatives. If you have a scheme of second order accuracy and you do a twice derivative, then you lose more or less all your accuracy you have there. Yeah? So it is always good when you can reformulate, and this is, as you can see here, a reformulation, clearly a reformulation without any approximation. Another nice trick has been done by Ribner, and you can show when you neglect the viscous term in the momentum conservation that the Laplacian of the incompressible pressure is exactly minus our light hill source term for the incompressible flow, which is quite nice in this sense, because when you use this relation, you just have to store a scalar. Yeah? Don't forget, we first do the flow computation. So you have to store all your flow quantities. At least we have to store the velocities, which are vectors. You have a x, y, and z coordinate component, for example. In this case, when you use this exact reformulation, you just have to store the incompressible pressure, which is a scale. So, and when I'm speaking of storing data for a fan, for example, as shown before, you will have computations, let's say, with about 20 to 30 million of volumes. Yeah, mainly you use the finite volume method for flow computation, and that you have to store for a lot of time step. Yeah, and a lot of time step, when I call a lot of time step, for most cases, in order to really resolve the most important scales of the turbulent flow, you have a time step size of something like 10 to the power of -5, which means you need 100,000 time steps in order to have computed for 1 second. And so your storage will be terabytes, yeah, for such a problem. And then clearly it's great if you can reduce it in this sense that instead of storing the velocity, you store the pressure. On the other hand, a good idea is also to compute on the fly during the CFD computation. You already compute your source term. Okay, one step further has been done in this sense by Powell as well as Ho, and it already goes towards vortex sound models to use now this reduced light hill tensor. Therefore, we have this L tilde here. So we are modeling the flow as incompressible flow, and by the vector identities, you can rewrite this term here, which is the double divergence on the light hill tensor. Just the mean density is in front because it's a constant. You can rewrite it by this first term and the second term. So the first term is the vorticity cross product with the incompressible velocity, and then this vector, from this vector you take the divergence. And the second term is the Laplacian of the incompressible velocity squared. And for most cases, and here you have to be a little bit careful, because this derivation you will also find in the book of Ho, which we cited in the script. This is more or less for flows around obstacles. Yeah? So if you have confined flows, for example, flows in a pipe, it is not as easy to show, and for most cases you even cannot show that you can neglect this term. But neglecting this term then gives you a subset of the approximate light hill tensor, and here the vorticity comes in, and this term here is a very prominent term. Why? Because you call this part here the so-called lump vector. Mm. So the cross product between vorticity and incompressible, or in general flow velocity, is the lump vector. So we see the divergence of the lump vector gives you the sources, and the nice thing is that we have really here the vorticity being in. So this is again, so this was the first simplification here. We restrict to low Mach number flows. We can model the flow as an incompressible flow, and then by vector identities we even take just a subset of this term here, and we call this term here then the typical vortex sound. There is even some extensions of it, but for vortex sound, more or less, this is the typical source term on the right-hand side of the wave equation. Okay, do you have any questions or comments? So you have seen now from a physical point of view, when we can restrict to low Mach number and we can model the flow as an incompressible flow, then this light hill wave equation makes sense, yeah, because we really separate the flow from the acoustic waves. We first can do a flow computation. We don't consider any waves in this flow computation because we consider the model of an incompressible flow. Waves need compressibility. And we have now different already ideas how to compute the reduced source term. This is now really a source term, yeah, because there is no interaction here between flow and acoustics. We can compute it also via the incompressible pressure and not only via the incompressible velocity. And taking a subset, we come to a source term being the source term for vortex sound. Okay, now let's go a little bit back and I want to show you the investigation of jet noise, the main noise term at this time. It was about 1952 and 1954. There were the two big publications of Lighthill, and he investigated the jet noise, the main source term of airplanes. And as you can see here, we have the model as a nozzle flow here, and the flow coming out and having here a strong turbulent region, and these are generating the sound waves. Now, as I already told you, at this time, numerical solving the inhomogeneous wave equation was more or less not possible due to the restriction of the computer hardware at this time. And so the idea of Lighthill clearly was to transform it into an integral equation, and then perhaps by considering far-field approximation, as we discussed in the acoustic chapter, he gets some nice formulas at hand to find out how much of the full flow power is converted into acoustic power. Okay, so since at this time Lighthill had not at hand, he wanted to have a simple formula. He considered now his problem in such a case, as you can see here, that he put away the nozzle because the nozzle would be an obstacle for the generated sound, and he just considers a domain of a lot of vertical structures due to the turbulent flow outside the nozzle. Yeah, and as we know, when we have such a source term for and free radiation, we can write down, now it is already written down for the pressure fluctuation. Still, it's not the acoustic pressure, it's the pressure fluctuation. With the simple relation that P prime is C0 squared density fluctuation. And as we know from our investigations in acoustics, that is now our term. You see that we have the Green's function 1 over the distance between observer position and source position. Here the 4 pi is in front of, and we have the retarded time. And since the source term is the second spatial derivative, we should not forget that we have here the second spatial derivative. This is out of the integral because we integrate over the y coordinate over our source coordinate. Okay, so this is now an exact reformulation of the inhomogeneous wave equation of Lighthill, however restricted to a case where, as shown here, we have free field radiation. So the nozzle has been taken away, and then we can use the Green's function of free radiation and get this integral. Now you can go towards far field approximation of this formula here, and there we know that we can, in this sense, the retarded time can be approximated by this term here, as we have discussed. The amplitude decay, we can approximate by just 1 over the position of the observer. So we neglect here the difference between observer position where we want to compute the pressure, acoustic pressure at the end, and the source coordinate. And furthermore, what you also can do is that you can substitute the space derivatives by a time derivative, again for the far field approximation. So you can, as you know, since we have here this argument of our light hill tensor, yeah, as shown here. And if you do a space derivative with respect to x, you can express this, since this is the argument, also by a time derivative. And then clearly the inner derivatives have to pop up. And that is the case why we get this additional term in front of, which is the length from the origin to the observer position. So it's the absolute value of x vector, and here you have xj. And since we have a double space derivative here with respect to xi and xj, we get also this double time derivative, and also this term here follows that we have the absolute value of x squared. Don't forget that we also have to take into where it is. Yeah, we also have this decay term, therefore we have the absolute value of x to the power of 3, xi, xj, speed of sound squared, clearly, because we have to apply this twice. And that is now a nice formulation. Still, we have here this retarded time. It's not so easy also to solve this, but in most cases, a time derivative is easier to be evaluated as a space derivative, which we have in this formula. So this is the exact formula as we know. And for far-field approximation, we can rewrite it. Therefore, we have this approximate sign here. We can rewrite it by this formula. Okay, and by the help of this formula, now Lighthill was able to get the very important scaling law to find out how much acoustic power is generated by one individual vortical structure. So here is the whole source domain. We have a lot of vortical structures there. You pick out one vortical structure with a typical geometric scale of small l, and we are looking for one of these vortical structures, how much acoustic power we get out of this flow structure here. So we have this vertical single vortex with length scale L and velocity V. The turbulent fluctuation is given by the frequency, which will be then proportional to this characteristic velocity over the length. On the other hand, we assume that we have a compact acoustic source, which means that this wavelength of the acoustic wave being generated is large compared to our length scale of the single vortex. We know the wavelength is computed by the speed of sound over frequency. Now we can use here this approximation, and since the characteristic velocity over speed of sound is the Mach number, and you have low Mach number, so for example 0.1, then we see that the wavelength lambda is at least 10 times of the geometric length scale of this vertical structure. Okay, so since we are acoustic compact, and we have to evaluate here this source integral, we assume that we can set this as constant. The source term for the individual vertical structure is L, that the domain size is L to the power of 3. That is why we get here L to the power of 3. It is proportional to the velocity squared, because we have Vi, Vj. And also here, this mean density is taken into account. We clearly also will have to consider these factors. yeah, which we will do. Okay, but just looking at our system, mean density Vi, Vj at retarded time. Since it is compact, we forget the retarded time, and we can rewrite it by this term. Okay, furthermore, a time derivative, yeah, is proportional to the velocity over L. Yeah, the characteristic velocity of the flow, which we already have used here for the frequency, 1 over frequency, then is the time scale, so it's velocity over L. Yeah, and that should give us the acoustic pressure, where this is now proportional to this term here. So what we have taken into account is clearly also this vector here. We assume that this is something like x squared. Here is x to the power of 3. So at the end, we will just have 1 over the absolute value of x. We should not forget also this c0 squared. Yeah, and that gives us at the end this formula for the acoustic pressure. So the acoustic pressure, as we see here, is proportional to the characteristic velocity of this vertical structure squared and the Mach number squared, or just expressed by the velocity, then it's proportional to the velocity to the power of 4. And we also have nicely the decay of the pressure with distance, which we see here by 1 over x. Now, we are interested in the acoustic power. And the acoustic power, clearly as we know, exactly written down, is the closed surface integral of acoustic pressure, particle velocity integrating over the closed surface. What I should also tell here, I already speak here of the acoustic pressure because we are in the far field. Yeah? And in the far field, our P prime approaches the acoustic pressure because at some distance there will be no flow, so the pressure fluctuations can just be the acoustic pressure because as we know, this decays with 1 over distance. The fluid dynamics quantities, as we already discussed, the vertical structures, vorticity and so decay with 1 over distance to the power of 3. Now again, we do here clearly some approximations in this sense. From here to here, we assume that we have plane waves. So the relation between particle velocity and pressure is simply given by mean density and speed of sound. Yeah, and now we just put in our derived acoustic pressure, and what we see is at the end that the acoustic power, so this part of the full energy in the flow, is now converted to the acoustic power, and that is, as we see, proportional to the velocity to the power of 8, or rewriting it with the Mach number, velocity to the power of 3, Mach number to the power of 5. So we see that this term we have considered here, yeah, will get large acoustic powers, but then we need a very high velocity. And for low velocities, we can strongly reduce it. Now, how can you use this concerning this jet noise? That was then reduced by the bypass, and due to the bypass, one could strongly reduce the velocity through the engine at the end, which means by this idea of the bypass, this jet noise being generated could be strongly reduced. And that was the idea of the bypass, because Lighthill was able, as shown here, to get this 8 power law, and it shows you by reducing the velocity, you strongly can reduce the generated acoustic pressure and then clearly as well the acoustic power. So this part of the power being converted from the flow to the acoustic. Okay, so are there any questions? So all details you will also find in the script when you really want to get also, for example, this very nice approximate relation between space derivative and time derivative. But you see again these important steps which we already discussed in detail for acoustics, that we have a possibility to get out of our equations a analytic formula, even if this is just an approximation. But in this approximation, we have the scaling, how the velocity scales, and how the acoustic power scales with the velocity, characteristic velocity of the flow, and so on. So this gives us really an insight and clearly also provides us with knowledge which we can apply for practical applications. So far, we have considered now problems where we have free radiation, which is clearly not the case, even not the case, yeah, for the problem at hand. Lighthill has investigated this jet noise, because we have here our nozzle, and we will have, when sound is generated, we will have here clearly reflections. So actually we should also be able to consider this. That's not the big problem when you solve the partial differential equation, but we also would like to have an integral equation which also includes any reflecting solid objects, and then perhaps get also for such a case a scaling law as we have obtained here for the typical jet noise where we assume free radiation. And that will be the next step we will discuss next time, so next week.